Let's now discuss capacitors in series and parallel connections. So you have capacitors, series, parallel. So we are talking about the parallel plate capacitors that we had seen in the previous chapter. So if you have one capacitor after another, so like this, you have n capacitors. So you have C1, C2, C3, C4, so on, Cn. So different values of capacitors, again, because they might have different geometries or they might have different materials inside, would lead to different capacitances. So once again, the general approach is take this system and then what do you say? Connect it to a battery, and then the battery has potential E, it gives a charge I, and then what happens here is in case of resistors, you calculated the ratio of E and I to get net resistance, but here it's not resistor, right, it's a capacitor. To get what net capacitance is, you need the ratio of E and Q, not E and I, right. So basically V by Q, Q by V. Q by V was nothing but your capacitance. So you need the ratio of Q by E. What is Q here? What this battery does is, in fact, let's actually see how a battery charges a capacitor. So if you have a capacitor here, so capacitor is like two plates of same length. This is your battery. So what happens is, when a capacitor is just kept isolated, it will have no charge. Once you connect it to a battery, immediately the battery will drop its E. What is E basically? It's EMF. So you can either write it as V or E. The E will drop here, and if the capacitor has a capacity C, then I can say the charge on this capacitor will be EC. It will be a plus EC on this plate. It will be a minus EC on this plate. So how does it happen? Like how does this charging happen? The battery, this positive terminal of the battery, takes a positive charge from this plate. It takes electrons, because anyways, as you know, only electrons in reality move. So this positive terminal of the battery attracts an electron from this plate. So if it attracts a minus E electron, so in fact if it acts one electron has 1.6 into 10 power minus 19 coulombs, right? So if it extracts one electron, that means this charge has become excess positive. So if you remove electrons from here, the charge the plate will become positively charged, right? And what a battery is doing, it's taking the electrons from this plate and it's putting it on that plate. So ultimately, it has taken as many electrons as are needed to create a charge plus EC. So this Q, nothing but your EC here. How did this EC come? Because it took an EC amount of negative charge from this plate and it put that EC negative charge on this plate from this terminal. So that's how a capacitor is charged by a battery. In fact, we'll see in RC circuits that when you have a resistor, this charging process might take some time. But if you have no resistor and you connect a capacitor to a battery, zoop, within a second, or in fact within a millisecond or within a microsecond, this capacitor will be charged. In fact, it will not take any time. You connect it, by the time you analyze what has happened, the battery would have taken this EC and it would have put that negative EC, and then I would say that the capacitor would be charged, and the potential drop across the capacitor would be E, and while its capacitance is C. So if you have a resistor, this charging might take time, but if you don't have a resistor, it will happen very quickly. So here also, let the battery drop a charge Q1 on this capacitor, Q2 on this capacitor, Q3 on this, Q4 on this, and so on up to Qn on this. So what does Q1 mean? Actually, what Q1 means is the battery has taken a plus Q1 from here and has dropped a negative Q1 on this. What do I mean by Q2? The battery has taken a plus Q2 from here and dropped a negative Q2 on this. Similarly, what do I mean by Q1? The battery has taken a plus Q1 from here and has dropped a negative Q1 on this. So now, as you know, if a capacitor has a charge plus Q on one plate and a minus Q on one plate, then I will say that the potential drop, if its capacity is C, I will say that the potential drop V is nothing but Q by C, right? Though there is a plus Q minus Q, but this is the formula, like this is the notation. The potential difference is Q by C. So here, the potential difference here is Q1 by C. The potential drop here across this capacitor. Across this capacitor is Q2 by C2, this is Q1 by C1. Similarly, across the nth capacitor, the potential drop is Q1 by Cn, right? Now, because this plate is at a positive terminal, and this is at a negative one, this is at a positive terminal, this is at a negative one. So like as if you move along this path, like if you apply Kirchhoff's law in this path, you are moving from a higher potential plate to a negative potential plate. Again here you are moving from a higher potential plate to a negative potential plate. For all the capacitors you are moving from a higher potential plate to a negative potential plate, because this positively charged plate is at a higher potential than the negatively charged plate. That's how we give it. That's the convention that we give it. So apply Kirchhoff's law here. Loop law, go in this direction, it will be a plus E, and then because it's all of them are in the decreasing like your direction, the direction in which you are moving is in the decreasing potential for all these capacitors. You'll add a plus minus Q1 by C1, you'll add a plus minus Q2 by C2. Basically you're just adding potentials, so on. You'll add a minus Qn by Cn, right? So now if I replace all this system with just one capacitor, such that neither my battery changes nor the charge, nor the net charge changes, right? So the net charge that was supplied by the battery here was Q1 plus Q2 plus Q3 plus so on up to Qn, right? So the net charge here is, this net charge is nothing but Q1 plus Q2 plus Q3 plus so on up to Qn. So what is the C equivalent? What is the C equivalent for this system? What you have to understand is this E is nothing but, so we have applied Kirchhoff's law successfully here. So if you get the ratio of QE is to net charge, in fact if you get the ratio of net charge is to E, you will get what is known as the net capacitance, right? The C net. So because this E would drop here and then Q by E is nothing but what your C net is. So from this equation also, like you have E and then you have all this Q1, Q2, Q3, Q1. Also remember one more thing, just the way, yeah, so in series, if you are moving in a series, your current does not change. Similarly, charge in a branch does not change, right? So in fact, you have to keep this in your mind. Maybe I just told that Q1 plus Q2 plus so on up to Qn is Q in this case, but that's wrong actually. In this case it is not. In the parallel case it would be. So in fact here I will say that Q1 is equal to Q2 is so on is equal to Qn is equal to Q, a common charge Q, right? Because the same current is flowing through all these capacitors, and then all of them will get charged at a time. So if this took a time delta t to charge, even this will take a time delta t, even this will take a time delta t. As we already know the same current is flowing, so I into delta t is basically the charge that was put on the capacitor, right? Because the current was flowing, I was the current, and delta time into current will give me the charge. So because I is same for both, and then all of them get charged at the same time, so that means all of them have equal charge on it. So remember, in case of capacitors in a series, charge will not change. So here it will be Q for all of them. So in fact, when I equate this to 0, I can say, solving this equation, E is nothing but Q times, I can take Q1, Q2, all of them, I can replace them with Q, take the Q common, and then I have 1 by C1 plus 1 by C2 plus so on plus 1 by Cn. And then here you have, what is your Q by E? Q by E is nothing but 1 by C1 plus 1 by C2 plus so on plus 1 by Cn. And then if I replace this with an equivalent system so that my Q also does not change and my E also does not change, then what will be the C equivalent for that? So once I just have to relate these two for that. So I can say that C net is nothing but this, or I can say 1 by C net is nothing but 1 by C1 plus 1 by C2 plus so on plus 1 by Cn. So do you understand? This is the whole case. In fact, as you see, for a resistor, if resistors were in parallel, if resistors were in parallel, then this formula, like the formula that you see here, is equivalent to resistors being in parallel, right? So if you have capacitors in series, it will have a similar formula as to the net equivalent resistors when resistors were in parallel. So make that observation here. So what happens when you connect, what do you say, the capacitors in parallel? So this is your C1, this is your C2, so on. If you have n capacitors connected in parallel, so if you have to calculate equivalent capacitance, once again what will you do? Just connect it to a battery with an EMF E. Now what will happen is, because all these capacitors are connected to the same potential, the potential drop V, because this is E and it has no, if it has no internal resistance, let it be an ideal cell, this E will drop on all these capacitors. So the drop on this capacitor will be E, the drop on this capacitor will be E, and then even on this, like drop on all these capacitors will be E. In this case, what will be different for them? The charge will be different for them, right? Because when current started flowing from here, the current in this, the current in these branches were different, right? It divided in a different manner. So when I do I delta T for all of these capacitors, it will come out to be different. So like the charge on this capacitor is Q1, the charge on this capacitor is Q2, so on, Q1. Only if the capacitors have equal capacitance value, the charges will have the same value, otherwise the charges will be different. But here in series, the charge on each capacitor has to be same, but the potentials are different. As you can see, the potential here is Q by C1, the potential here is Q by C2, the potential here is Q by Cn. Q and Q2 are all equal to Q. So potential drops here are different, potential drop here is same. It's same as resistor. The potential drops in series are different for resistors and capacitors. The potential drops in parallel is the same for resistors and capacitors. The only difference is, I will say in case of resistor, the current in the series is the same. In case of capacitors, I'll say the charge in the series on like two capacitors in series will have the same charge. Here I will say that two resistors in parallel will have different currents, but in case of capacitors, here I will say two capacitors in parallel have different charges. So understand this difference. So now I can say that Q1 is nothing but what do you say? It's nothing but E times C1, Q2 is nothing but E times C2. Similarly, Qn is nothing but E times Cn, right? So now if I want to calculate the net capacitance, I'll replace this by a single capacitor such that the net charge on the capacitor is Q, right? And then its net capacitance is C. So, and the battery also shouldn't change. So try to understand here. What was the net charge that the battery supplied here? It supplied Q1 plus Q2 plus so on up to Qn. When you add all these charges, that is what the battery supplied. Here you will not add Q, you will not add Q for all of this, because the net charge that the battery supplied was basically your Q, what do you say, it was Q. But here the charge supplied by the battery is nothing but Q1 plus Q2 and so on. So the difference here is the battery took charge a plus Q only from this plate, and it put a minus Q only on this plate. The rest of the charges that you see, they just came out, or you could say it was only a result of the distribution of charges, such that the net electric field in this plate, in this plate, in this plate, in all of these plates is zero. Like we already saw that before. Why does the charge in a capacitor distribute? So that the net electric field is zero. So here the battery only supplied Q. Don't think it supplied Q, like it didn't supply NQ here. It supplied only Q, because it only took a Q here and it put that minus Q here. And then others were only a result of distribution. But here your battery has supplied Q1 plus Q2, like all these charges your battery has supplied. So because the battery took charge from this plate, from this plate, from this plate, because all of them are connected to the battery, and it put an equivalent negative charge on this plate, on this plate, on this plate, and on all the plates. So that's why you have to add up the charges here. So I can say the Q net here is Q1 plus Q2 plus so on up to Qn. And then the net Q you can say here is nothing but E by C. sorry, it's E times C net. Simply you just have to, again this is coming from Kirchhoff's law, like I can say that plus E and then let it be plus minus with a charge Q, minus Q by C net is equal to 0 because we're moving in the direction of decreasing potential, that's why this negative sign. So E times C net is Q, that's what I'm putting it here, and then you can write EC1 plus EC2 plus so on plus ECN. And then cancelling E's on both sides, you'll say that C net is equal to C1 plus C2 plus so on plus Cn. So if capacitors are connected in parallel, this is the formula for net capacitance. This is something like resistor, the equivalent resistor when resistors were in series. So remember, resistor in series, capacitor in parallel have the same formula, like equivalent formula, and resistors in parallel and capacitors in series have the similar formula. So remember this, and with this we are done with the method of equivalent capacitances. So that's how, like, even in a, what do you say, in a complex system, when you have a complex connection of capacitors, complex capacitor connection, when you have something like this, and you want what is the net capacitance of this whole system, what you have to do is you have to connect it to a battery, calculate how much charge the battery supplied, Q, on all these. So here also the net charge was Q, and then here the net charge was Q1 plus Q2 plus so on up to Qn. So calculate how much charge your battery supplied and then take the ratio of the charge and E to get net capacitance. For this you obviously have to use Kirchhoff's laws, just the two Kirchhoff's laws and all the various loops and all that would be there in this circuit, and then solve the equations to get this. So again, it's easier said than done. You have to practice a lot. And equivalent capacitance or equivalent resistance, again it's an important model from the exam point of view. So look into such problems. And now let's move on with RC circuits.